so let's look at the continuation of section 4.7 with those optimization problems. Yesterday they kind of went through a 5-step process, 6-step process with us of a way that we could attack these. And so we are looking at example 4 today, page 281, example 4. All right, so they tell us a man launches his boat from point A on a bank of a straight river 3 kilometers wide, and he wants to reach point B 8 kilometers downstream on the opposite bank as quickly as possible. He could row his boat directly across the river to point C and then run to point B, or he could row directly to B, or he could row to some point D between C and B and then run to B. If he can row at 6 kilometers an hour and run at 8 kilometers an hour, where should he land to reach B as soon as possible? We'll assume that the speed of the water is negligible compared with the speed at which the man rows. All right, the first thing that they tell us is that we need to read the problem until we understand it. That might be one you read a couple of times before you really understand it. Do what you need to do, specifically looking for what am I trying to find. All right, so they told me that we are at point A and our goal is to get to the opposite side of a river that's 3 kilometers wide, and we want to get to point B. So I'm going to start over here at A and I'm going to try and get to B, but there are several ways that I could do that. I could row straight across the river and run the whole 8 kilometers down the side of the river. Or I could row directly from point A to point B and not run at all. Or I could do some combination where I row across to maybe some midpoint in between C and B, and then I run the rest of the way down. I want to see how to, it says, where should he land to reach B as soon as possible. So what am I trying to do? Am I finding a maximum or a minimum? Minimum. And what am I trying to minimize? The time. Yes. So I need to create an equation that deals with time in relation to the other components that they've given me in this problem. And in this problem, they've talked about distances and they've talked about rates. So it makes sense then that I'm going to use distance is equal to rate times time, right? Now, I can take distance equals rate times time and solve it for the time, since that's what I'm looking for. So if I divide both sides of that by the rate, then I'll get time is equal to the distance divided by the rate. All right? So the second thing that they suggest to me once I read the problem, make sure I understand it, know what I'm looking for. The second thing they suggest to me is that I draw a picture. Now, they were kind enough to give us a diagram here so we know what we're looking at, and I've got that diagram. But I want to analyze that a little bit further. I want to look at this triangle right here in the center. So I've pulled it out so that we can look at it a little more. They told me that the width of the river was 3 kilometers, and what they've asked me to find in the problem is where do I need to land to reach B as soon as possible. So if possible, for my setup, I want X to be where I need to land on the shoreline. So I'm going to call this distance on my triangle, I'm going to call that X, where X would tell me where I need to land. Maybe I need to land all the way up here to run the whole way. Maybe I need to land down here to not run at all. Maybe I need to land some X distance down the shoreline and then run the rest of the way. But by expressing that quantity as a variable, I cover all of those scenarios, because X could be 0 if I come straight across, or X could be 8 if I row the whole way down, or X could be some other quantity in between if I land at D and then run the rest of the way. So I'm going to call X that variable that would express how much of the shoreline I cover by rowing across the river. If this distance then is X and the total distance along this shoreline that we're working with is 8, then this distance will have to be 8 minus X. if x is the distance on the shoreline that I cover by rowing across the river, and the total distance I have to cover is 8, then the distance that I would still have to cover by running could be the total distance 8 minus the distance that I covered by rowing, 8 minus x. Again, we're not boxing ourselves in, because that still enables me to let, if x is 0, if I rowed straight across the river, that would still enable me to run the whole way. Or if x is 8, because I rowed all the way down to b, 8 minus 8 would still give me 0, that I didn't do any running. Or it would enable it to be some quantity in between so that I could do a combination of the running and the rowing. Okay? So again, we still have all of our scenarios available to us. So if this is 3 and this is x, then I could use Pythagorean theorem to find my hypotenuse, and so that's what we've done right here. We've said that 3 squared plus x squared is equal to our hypotenuse squared, and so take the square root of both sides and we'll end up with that hypotenuse being the square root of 9 plus x squared. Okay? Now, if part of my time is going to be spent rowing and part of my time is going to be spent running, then when I'm looking for an equation for time, my total time is going to have to be a combination of those two things, right? So let's go through and let's think about what rowing time would be and what running time would be, and then we can combine those to get our total time. All right, so let's think about rowing time. Again, time is distance divided by rate. So let's start with our rowing distance. If my rowing distance is what I come across the river here, remember that was our hypotenuse, and we had just found that to be the square root of 9 plus x squared. And then our rowing rate was given in the problem. It says that he can row at a rate of 6 kilometers per hour. So there's our rowing time. It's the rowing distance divided by the rowing rate. All right, running time, I need the running distance divided by the running rate. So let's start with the running distance. We said that after he lands, wherever that might be, that whatever distance was left to be covered would be that 8 minus x. So his running distance will be the 8 minus x. And they told us that he runs at a rate of 8 kilometers per hour. So our total time is just going to be the combination of those two things. All right, so if we're going to minimize our time, remember that your absolute minimum can be found at an endpoint, or it can be found at a relative minimum, which we're going to identify with critical numbers, right? So in order to identify our endpoints, let's think about the domain of x. Now, we've said that x is the amount of shoreline that he covers by rowing. If he rows straight across, then he covers no shoreline at all, right? He's going to have to run the whole 8 kilometers. So the smallest value it could be would be 0. The opposite extreme is if he rows the whole way down and doesn't run at all, then the distance on the shoreline that he would cover by rowing would be the full 8 kilometers. So those are going to be my extremes. Those are going to be my endpoints. And now we need to find our relative minimums with our critical numbers. All right. So for critical numbers, we're going to need to go through and take the derivative. All right. So let's think about that for just a second. I'm going to rewrite our equation up here just a little bit. I'm going to go through and pull this 6 out so we'd have 1/6 out in front. And I'm going to rewrite our radical. Instead of the square root of 9 plus x squared, I'm going to write it as 9 plus x squared to the 1/2. A little easier to do chain rule that way. And then for this guy, I'm going to break this into 2 separate pieces so that I can simplify it, as opposed to having to maybe do like a quotient rule or something like that. So I'm going to go through and just put the 8 over 8 and the negative 1x over 8, or negative 1/8x. So I haven't taken a derivative or anything yet. I've just rewritten our original equation to make it easier to take the derivative. All right, so I know that we are fabulous at derivatives, but I also know that we just had a nice long break, so good review for us. So if we go through and take the derivative of this first piece, I'm going to use power rule and I'm going to use chain rule. So I'm going to say 1/2 times 1/6 to get 1/12, and then keep the quantity exactly the same, and subtract 1 from our exponent. So there's the derivative of the outside. And then we need to take the derivative of the inside. So the derivative of 9 would be 0, and the derivative of x squared would be 2x. So there's the derivative of the inside. All right, then 8 over 8 is just 1, so the derivative of 1 would be 0. And the derivative of negative 1/8 x would be negative 1/8. All right, if we do 1/12 times 2x, that would give us 2x over 12. And I'm going to go ahead and move my radical down to the denominator to get rid of that negative exponent. And then we've still got our minus 1/8 over here. 2/12 would simplify down to just 1/6 x, and I could combine these two pieces. So I think that's probably about as simplified as I could get that derivative. And so that's the derivative that you see up here that we're going to use to find maximums and minimums. All right, so if we're going to take that derivative and find critical numbers, we're going to set it equal to 0, right? So I'll set that equal to 0. I'm going to go through to solve that. You could solve that any way you want to, but I'm going to go through and move my 1/8 to the other side. And then I'm going to cross multiply. Anytime we have an equation with a radical in it, we always want to isolate that radical so that we can square it. So I'll divide both sides by 6, and then I'll square both sides. So I'll multiply both sides by 9 to get rid of my fraction, or you could think of it as cross multiplying as well, either way you want to go. Get all my x squareds on one side, so subtract 9x squared. To get x by itself, I'm going to have to divide by 7 and take the square root. And don't forget, when you insert a square root, to insert your plus or minus. Now, x represented a distance, and distance can never be negative, so we're going to stick with just the positive value. Even though that's our only critical number, we do still need to check and make sure that it actually is a minimum. So we're still going to want to use our first derivative test. I'm going to get a decimal just so I kind of have an idea of where to plot that thing on a number line, but we do want to give the exact answer, not the decimal approximation, anytime that we can. So if we plot that and we pick a test point, I'm going to choose 0. Since I'm trying to create a sign graph for the derivative, remember I plug into the derivative, not the original. So if I plug in 0, I get a negative value. Cross a single critical number, the sign changes, or you could test a point on the interval on the other side as well to find out that it's positive. All right, so because our derivative changed from negative to positive, then we do know that we've got a relative minimum there. We're not justifying here, but just a reminder for the AP exam, if they say justify your answer for the relative minimum, you're going to say that for the values less than 9 over the square root of 7, your derivative was negative, and for the values greater than 9 over the square root of 7, your derivative was positive. Therefore, you have a relative minimum at 9 over the square root of 7. All right, so I need to find my absolute minimum by testing each of my endpoints and by testing that relative minimum that we just came up with. All right, so let's start by plugging in 0. Now remember, what we're talking about here is if x is 0, that means I rode straight across and I ran the whole way down. Now his running rate is faster than his rowing rate, so that makes sense that that might be a good thing. get across the river as fast as you can because you run faster than you row. So let's try that scenario. I'm taking that 0 and plugging it back into the original equation up here. 9 plus 0 squared is going to give me the square root of 9. So that's going to give me 3 over 6, or 1/2. And then if I put 0 in the place of x in the second half of this equation, 8 minus 0 over 8 is just going to give me 1. So that means that we rowed for a ½ hour and we ran for an hour, so altogether it took an hour and a half. All right, so then let's try the next scenario. If we're putting 8 in the place of x, then we're saying that he is rowing straight from A to B. He's covering the entire shoreline, 8 kilometers, by rowing, so there will be no running time. So if we plug 8 back into the original equation, so putting 8 in for x, putting 8 in for x, we're going to get 9 plus 8 squared, or 9 plus 64, so we'll get square root of 73 over 6. And then here, 8 minus 8 would give us 0. So again, as we said, there would be no running time because you're not running. The entire thing is done by rowing. So you can see that's actually a little bit shorter, even though he runs faster than he rows, because the shortest distance between 2 points is a straight line. So that's a plausible solution as well. And then the last thing we want to check is that relative minimum that we came up with. So let's plug that back in to our original equation, and we get 1.331. So if we're looking for the absolute minimum value, that is our lowest time. It takes 1.331 hours if I row from point A over to a point D, where x is 9 over the square root of 7, or 9 square roots of 7 over 7, or about 3.4 kilometers. Basically, I want to row to a point that's about 3.4 kilometers down, and then I want to run the rest of the way. Now, it's important with the word problem that you answer the question that was asked. So if you go back and look, it asks you, at what point on the shore should you land in order to minimize your time? So that's literally just going to be our x value. Where do we land? We land approximately 3.4 kilometers down the shoreline, or 9 square roots of 7 over 7. And so that's the answer that we want to give. All right, so here is our homework for tonight. On page 283 to 284, just doing a couple more of these. 39 is very much like example number 4. And your challenge number 19 would be like example number 5 if you want to play around with that one. And then, of course, we're doing 29 as well. So if I put 0 in right there, I'm going to get the square root of 9.